right, welcome back everybody. Today is Performance Day. I'm super excited, and a lot of other people are too. When we had the registrations, we had everybody kind of say in the registration what you were interested in, and this was absolutely one of the most popular topics. Everybody wants to talk about performance. Everybody wants to know about performance. So the way I'm going to structure today is a little bit different from yesterday. Yesterday we kind of had two big blocks, and we started with kind of a high-level overview, then we went deep. Today it's going to be a little more interspersed. So we're going to kind of go back and forth between some kind of higher level topics, and then some sort of very specific, more in-depth things. So, and it'll all be kind of mixed together. And the first thing I want to talk about today is, at a high level, just monitoring. As we talk about performance, I think the baseline, the starting point, is having the data to be able to observe how your system is doing. In the RDS world, so a lot of this class is Postgres. It's not RDS specific. We're talking about Postgres. We're talking about Postgres when you compile it yourself, Postgres when you use it in RDS. Even we're going to talk about Aurora. But the common theme is Postgres. But for just a minute, I'm going to go really specific on RDS. So in the world of RDS, there's basically a four-pronged strategy that you should have for keeping track of your Postgres systems. And the four-pronged strategy is performance insights, enhanced monitoring, CloudWatch, and then custom monitoring that you do outside of that. And this would apply whether you're talking about Aurora or whether you're talking about Postgres and RDS. But these are the tools that you have. And this should be the way that you think about monitoring. This should be the way that you think about having the data on how your system is doing. So what I'm going to do first of all is just kind of briefly walk through the four-pronged strategy. Just get this picture, like solidify it. I think it's just a good visual that there's these 4 points. And this is your attack strategy for understanding the performance of your system. And they're in order, by the way. I put Performance Insights on the top because Performance Insights, I would argue, is the most important tool that we have. Performance Insights visualizes the activity, I should say, not the load, the activity on your system. There's a lot of really good science and really good theory and years of experience that goes into building this tool. A lot of industry experience that has gone into building this tool. And it's very effective. So top SQL, kind of being able to drill down. One other sort of thing that I would point out, depending on how much you use Performance Insights, recently they added countermetrics. So if you haven't used those before, that's something you want to look at and sort of learn a bit more about. You have a lab environment. You should have. I hope that everybody was able to get the lab environment set up. In the lab environment, I hope that you caught the step where you turned on Performance Insights. That's a great place to go fiddle around because you have a workload running. You can look at PI, and what you'll see when you go to the screen. We'll spend more time talking about PI later, but the metrics that I'm talking about are above the graph that's in the picture here. So in the picture, I have the graph of active sessions. What you're going to see now when you go to PI is above that, you'll see another graph it'll probably have the commit rate. But there's a little gearbox next to that graph, and you hit the gearbox, and you've got access to like 30, 50, I don't know, a whole bunch of metrics both inside and outside of the database that you can graph. So that's PI. And this is if you're only going to know one thing, it should be PI. But we're not going to stop there. We'll keep going because there are some other useful tools as well. Enhanced monitoring has been around for a really long time in RDS, and PI does not yet replace enhanced monitoring. Now, when PI added those countermetrics, they actually added a whole bunch of the same OS metrics that are in enhanced monitoring. So it's kind of interesting to see that overlap. And I think something you can probably extrapolate from that is that we're investing a lot in Performance Insights, and you can expect to just continue to see investment in that. It's a well thought out, fantastic product. But it doesn't replace enhanced monitoring, at least certainly not today. One of the biggest reasons being the process list. So enhanced monitoring is continually capturing snapshots. It's like running top on your Unix box. It's continually grabbing these snapshots of all the processes that are running right now with whatever frequency you set. So I generally suggest to people with enhanced monitoring, like there's so many times I've gone into a system and I see it at 1 minute granularity, and it drives me crazy. I'm like, no, CloudWatch already has 1 minute granularity on a whole bunch of these metrics. Like you know, do better, like enhanced monitoring. So I often tell people like at least 15 seconds, if not 10 or 5, sometimes even 1. The trade-off is just data volume. I've never seen performance overhead be an issue with enhanced monitoring. The only kind of consideration probably is just if you're running every 1 second, it is going to store all that data in your CloudWatch account. But this is the sort of data that I usually want to have, and it's absolutely worth the cost, right? It's giving you performance information about your database. This process list turns out to be super useful as you kind of want to go back in time and look at what was happening on a system. To use performance insights with RDS Postgres, you need to be on at least Postgres version 10. And so when I bump into people who are still running older versions of Postgres, another thing to point out is that enhanced monitoring is the only thing that you've got. You don't have PI. So this is an important tool as well. Thirdly, CloudWatch. CloudWatch, you know, I hope that everybody is familiar with it already. It's still a really critical tool. So getting familiar with one of the most important things about CloudWatch. So we have a whole bunch of CloudWatch metrics, and you're probably aware of that. But the really, really important thing about CloudWatch is what you can do with that data. CloudWatch is very easy to plug into a whole bunch of other things, right? In particular, alarming is like a big one. So CloudWatch is the place where you should be setting up alarms on sort of important metrics. Metrics like disk free, so you don't run out of space. If you're on RDS Postgres, it will not automatically grow your volume. If you're on Aurora Postgres, watching the amount of local storage, that is a metric that you have in CloudWatch that you can alarm on. Things like memory usage. Another really cool thing with CloudWatch, worth pointing out, is that Performance Insights actually exports metrics to CloudWatch. In particular, you can see the DB load, and then it'll also give you 2 more metrics, one that tells you just the DB load of processes that are on CPU, and then DB load processes that are waiting. When I was a DBA years ago, I remember doing this with Oracle Enterprise Manager, and I had to write a bunch of custom code to get this to work, but I figured out how to write some code to calculate the average active sessions over a 5-minute window across every database in our fleet with OEM, and then we built an alarm on that. And I remember once we had that alarm in place and we kind of had it calibrated, we knew there wasn't a single time. So first of all, I don't think I ever had a false alarm. Whenever I got a page, it was legitimate. Something was going on. And secondly, there was never anything that happened in our data centers that I didn't know about at first. So every time a developer or somebody complained, and it was almost always that DB load. This is a fantastic metric to alarm on and to watch to know when something's going wrong in your system, performance-wise. Because when things start to get slow, what almost always happens is you start seeing the number of connections go up, and you start seeing applications do more, and what ends up happening is the number of active sessions climbs invariably. And the great thing about this DB load metric is that so the other thing that people usually think of is CPU, like I'll put an alarm on my CPU, and that catches some problems, but there's a lot of problems it won't catch. Basically, anytime you're off the CPU, waiting for a disk, waiting for a lock. This DB load metric is great because it catches a lot of stuff. And then last but not least is custom monitoring. And basically the point here, and this is actually, I think, really important. The point here, we have really good tools. We're continually working to make our tools better that we give to customers so that you guys are able to work with customers and recommend to them. At the same time, like we're running real production workloads on these databases, and even like there are some awesome things that the Performance Insights team is going to have out like this year. But you just can't wait when you're running a real production system. You need that, you need this data now. And you need to so there's a couple of things I would point out that sort of I continually find myself telling people that you should have that I'm sure it'll be provided eventually, but you can't wait. One of the biggest things is like getting regular snapshots of performance data inside of your Postgres database, just somehow. There's a lot of different approaches, ways you can do this. There are even some third-party tools as well, or you can do it yourself. I've seen people take a lot of different approaches. But like for a real simple example is just SQL statement statistics. And I remember just yesterday pointing somebody toward this when they asked a question about how to do some troubleshooting on one of their systems, is that Postgres can keep SQL statement statistics. So for each SQL statement that it sees, it can tell you how many times has that SQL statement been executed, how much I/O is that individual SQL statement doing, how much time is that SQL statement taking to run. So I executed it, but it run in 1 second, or did it run in 20 seconds, or did it run in 10 minutes? It captures all that information. In order for you to make use of that, for it to really be useful, what you need to do is, so what Postgres tells you is just sort of the totals. They're counters. They just increment over time. So it'll tell you the total, since the database started up, how many times has this SQL statement run. What you really need to know is what was going on at 2 o'clock yesterday afternoon when the whole system spiked and things went crazy and I had an application incident. In order to know what happened at 2 o'clock yesterday afternoon, you need the snapshot from 1:45 and the snapshot from 2:15, so you can just do a little bit of math and subtract the numbers. And you can see which SQL statement was the one between 1:45 and 2:15 that shot through the roof. That's one example, but there's a plethora of statistics that are inside of Postgres that are worth capturing and are worth hanging on to. So this is in our happiness hints, and this is something that I'm getting bolder and bolder about telling, just coming right out and saying this to people over time, that look, you should just be capturing this information, especially the SQL statement stats are really useful. So that kind of leads into one thing that's worth kind of taking a moment on, just because it comes up so often, which is kind of in sort of Oracle parlance or Oracle terminology, there's these two sort of very closely connected ideas of an AWR and an ASH. Are you guys familiar with these ideas? You are, you aren't. So a little bit of yes, a little bit of no.
AWR, yes, but ASH.
Okay, so it's basically, they're very closely related. The AWR is kind of what I was just describing a moment ago, of capturing, fundamentally, at the bottom layer is capturing data. And Oracle has a similar concept. There's these metrics, which are just counters that increment. And they capture a snapshot. I think the default is every 15 minutes, if I remember correctly, but I'll have to double check that. But it grabs those snapshots. And then they have some canned reports that come out on top of that, some really useful reports. The ASH is a similar idea, but that stands for Active Session History, and that's specifically looking at sort of Oracle's equivalent of pgstat activity. And that samples at a high frequency, once a second. So that ends up being very useful for a couple of other reasons. It's a really common question that I hear people asking, just how do I get this? There are multiple efforts that people have made, and I also know lots of people that have gone and done their own thing, but it's worth sort of taking a moment on a slide just to point you towards some of the names that I keep hearing about a lot. So I absolutely think this is a very good question in the right direction to be thinking. I spent many years working very deeply with Oracle, and these are essential tools. When you're maintaining and running a database, you need that data. You need that tactical intelligence about what's happening inside of it. And these are probably, I would say, the two most important tools in anybody's toolbelt who has worked with Oracle. So you should be asking, how do I get this in Postgres? I don't think that the sort of Postgres world at large has coalesced yet around sort of a preferred approach to this. So there's still a number of people working on it. Three of them that I listed here are the Postgres Workload Analyzer, PG-StatsInfo. So POA, POWA, is kind of an open source project that my observation would be that there seems to be a good bit of a community around that, and it seems like I see things happening there quite a bit. PG-StatsInfo comes out of NTT in Japan. They do some really good work. It's not as transparent. It's not so much like an open source community-driven thing. It's more that there are a development center, think of them like HP or Dell, who just does a bunch of work, builds something really awesome, and then just publishes the code. And that's what they've done. They've just kind of published it. It's a permissive license. You could take it and use it, but it's not so much that like they're looking for people to submit patches or anything like that. They're just publishing some really good work they did. PG Sentinel is another really cool product that's developing quickly. Some folks in Europe coming from sort of an Oracle background, going deep on Postgres and sort of bringing that perspective to it. This, by the way, on the bottom here is what the report looks like out of POA, just to kind of give you an example. It's like this is one section of it, but it's just listing the top queries, and it's telling you you can see that you can sort by execution time, by the I/O time, by how many blocks were accessed by these queries. Over on the right is an example of the StatsInfo report. And one of the nice things about StatsInfo is that they've actually taken the time not only to build the data collector, but also to build a canned report. Their canned report, that's, if you've seen an AWR report, that's what the top of an AWR report looks like. There's a summary of the system, then there's a workload summary right at the top, which is like their database that shows you like the commits, average commit rate, the log generation rate, sort of some high-level stats, and then it drills down from there. And they take a similar approach. So that's a bit about the AWR and the Ash. All right, that was my high-level sort of spiel on specifically monitoring and RDS specifically, and then sort of at the end here, kind of stepping back and looking at a particular use case in Postgres. What I'm going to do next is just quickly hit on two quick hit topics, and then I'm going to take sort of a short break and then dive into what I think is the most important thing for the remaining time. So my two quick hit topics. First one, super fast, but I didn't want to skip this because it's just too important of a thing to mention, which is explicit locking. So there's two kinds of locking in Postgres. You have sort of a locking that's very low level. Think of this like sort of like semaphores or like a Linux kernel has locks. In Postgres, those are called lightweight locks. And they're things that are used for concurrency control inside of the engine. They're never held for a long time. But for example, protecting a bit of shared memory so that you don't have multiple processes, somebody like reading it while somebody else is writing it. If you have shared memory, you have to have concurrency control around multiple processes accessing the same things. Those are lightweight locks. That's not this. The other thing that you have is sometimes in the Postgres documentation, I've seen them referred to as heavyweight locks. I've also heard people say transaction locks or SQL locks, but it's kind of more of an application level locking type of a thing. And this is like when you update a row, okay, that row, you would take a lock on that row. And that's the right thing. That's actually what you want. I always feel like I have to point that out now because sometimes with some of the dialogue around massively parallel systems and sort of NoSQL and different storage models, sometimes we get an idea that like just locking is always bad or something to be avoided. But if you have, just to give a really simple example, if I just have like, I have a value 3, all right, and I want to add 1 to it. Okay, so I want to say increment that by 1, all right, and then I have somebody else, and he wants to increment it by 1 at the same time. Well, the first guy, he increments it from 3 to 4. But until he commits, you don't know, right? Is he going to abort or is he going to commit? Is he going to crash or is he going to succeed? Is there going to be some failure in this process? So the other guy, like, what should he do? So he wants to increment the value too. Should he store a 5, because it was incremented to 4, or should he store a 4, but then the first guy is going to store a 4, right? You can basically you can start losing data if you don't, if two people are modifying the same thing. You don't want those to happen at the same time. Like, what you actually want to happen for exactly the same value is you want those to happen in order. You don't want it to get confused and lose the data. So that's what locking was invented for, and that's the right use case for locking. And that's what this is about, explicit locking. So Postgres, my goal here is just to point you in the right direction so that you can find what you need to know when you need to find it. In Postgres, you've got 7 different types of locks that can happen on a table and 4 different types of locks that can happen on a row. So locking can happen at a table level and it happens at a row level. When we did the sort of introductory architecture thing, one of the things that we said is that writers never block readers and readers never block writers. That is true mostly. Well, and you said in the context of DML, and that is true entirely. That's right. That was qualified. It was qualified correctly. So in the context of DML, writers never block readers. Readers never block writers. DML, if you're not familiar with the acronym, stands for Data Manipulation Language. It just means inserts, updates, and deletes. That's what that means. And we use the acronym DDL for Data Definition Language for all the things like creating tables and dropping tables, things that change your schema. If you're not familiar with the SQL lingo, it's worth pointing that out. So we have 7 different ways of locking tables, all right? And there's 4 ways of locking rows. And the place to go is there's a chapter in the Postgres docs called Explicit Locking. And someday, when you're in a situation where you need to learn a bit about locking, this is the place to go. So it's chapter 13.2 in the current version 11 docs. I feel like the chapter numbers change sometimes over major versions when they add new chapters. And I have found that it's never obvious to me where this is from the table of contents. So I'll just tell you, I usually just type in explicit locking in the search bar, and that's how I find it quickly. It's not tied to a SQL command or anything like that, but there's a particular page called explicit locking. This is a screenshot from that page. And you'll see there's kind of a matrix of which lock modes conflict. Now, the one other really great thing that they do is with these 7 ways that you can lock a table, the Postgres documentation, which is fantastic, actually walks through each one of those and tells you exactly which SQL statements use that locking mode. And I want to highlight just one because it's very important, and that is there's the locking mode back here called access exclusive. It's at the very bottom, and you'll notice that access exclusive conflicts with every other lock mode. So what that means, if it conflicts, that means that so if one person wants to get a table in exclusive mode and somebody else is trying to lock the table in the access share mode, they both can get the lock. That's not a conflict, so they both can have the lock at the same time. However, if somebody has an exclusive lock on the table and they want a row share lock, there's a conflict. So they'll have to queue. They'll have to wait. So they queue up, they wait, and whatever the operation is will pause. And once the operation with the exclusive lock finishes, and another important thing, by the way, these are transaction level locks. So when you lock something, you either have to explicitly release the lock. And then for sure, if you commit or roll back the transaction, that will release your locks. So they often operate at a transaction level, maybe always, but I'm not sure on that. I should double check that before I say it on a video. So that's what the conflicts, that's what the X's mean. it looks kind of like a line. It's not exactly a line. You'll see there's kind of some weird jumps and there's a hole in the middle. Share locks are not, a share lock does not conflict with a share lock. So it all kind of makes sense, and this has all been carefully thought out to basically get as much concurrency as possible in the database. It's the reason you have 7 different lock modes is that it allows us actually a ton of flexibility to let a lot of things happen without needing to wait for other people. But then there are certain things where you do need to wait. Like, I mean, the example of, the modifying the same exact value, like that's by design, that'll never change. If 2 people want to change the same number, you're always going to want those to go one after the other. So the one access exclusive lock, this is the guy who blocks everybody. And this is the one exception to the readers and writers rule, and they even call it out in a tip. Only an access exclusive lock blocks a select. So that has massive implications, right? If you do an operation that needs this lock mode, it will stop everything on your database, everything. And they list out a couple of these. Okay, so some of these are obvious, and some of these are not really problems per se. Drop table, I mean, like, okay, if you're dropping the tables, probably nobody should be running selects on it anyway, so fine. But the ones to look out for, the one to really look out for is this little sentence, many forms of alter table. But they don't actually tell you all the ones. If you ever look at the documentation for alter table, it's like alter table and there's like 50 different things you can put after alter table. And what they're saying here is that some of those things require an access exclusive lock, others don't. And another thing, kind of over time, Postgres has continually worked to whittle this down. Another thing you'll see, like the reindex command uses an access exclusive lock. This is one of the reasons we talk about using create index concurrently, because that is the alternative way to get a new index or to rebuild, to replace an index that has an issue without needing this level of locking. So when you bump into something, go find this section of the Postgres documentation. It's well written. It'll get you through. This came up yesterday, and I realized that it was an important enough topic to actually pull some stuff out that I was planning to talk about today and replace it with this. And it's the idea of reusing execution plans. Also, yeah, I'm still wrapping my brain around this a little bit. I went back last night after the conversation we had yesterday and kind of got a refresher on some of this and realized that about 2 or 3 of the things I said were completely inaccurate. So I also want to correct that as well. But this is a really important topic. Now, first of all, I'm going to start by telling you where to go, or where I went, and what seems to be the best starting point for figuring this out. And that's the prepare command, the documentation. So I will always send you the Postgres documentation. The Postgres docs are very well written. They're very good. One kind of unique thing about Postgres that I haven't seen in many other open source projects is that the documentation is part of the source code. So it's checked in to the source code repository. The same people that maintain commits for the database source are the same people that also have to either accept or reject the patches and the commits for the documentation. And in Postgres, the Postgres development community is very rigorous when it comes to, well, you'll see both commenting the source code, following, like having clean, readable, following a certain format with their source code, as well as making sure that this documentation is accurate and stays up to date. I mean, you'll see a patch come in, and then you'll see the docs have to be updated before this patch can even go into the source code and be committed. Like the patch needs to include the doc update along with the code update. So the docs are good, and I point people to the docs frequently. So this is where to go, and this is where I started. This is the best starting point. But let me just sort of walk through what I've learned so far. First of all, I'm going to revisit something we introduced yesterday. This is talking about what happens between your application or your client and the database. And we kind of introduced this thing yesterday, right? That we have You have your client applications. Your clients are talking to the database, and there's a lot of different kinds of clients is kind of what I wanted to catch here. That we have Java stuff that maybe uses JDBC, which speaks to the libpq wire protocol, talks directly to the database. You have things like the PSQL command line program or Perl, Python, whatever, that use the libpq library. Another thing that wasn't on this picture, but I wanted to point out, is that you also have in-database languages as well. So things like PLPG-SQL, Perl, some other things. Tickle is in there. There's a number of languages that can run inside of a Postgres database as procedural languages. And they also need, well, for what we're about to talk about, they have a database connection as well. What are these clients doing? Right? We have this little arrow between the clients and the database, but what is that arrow? Let me zoom in on that arrow, sort of borrowing another slide from Boost Momjian. That arrow is clients are sending queries, right? And then the database server is sending results back. Like largely that's what we're talking about. We're talking about sending SQL statements, sending SQL queries, and results going back and forth. And what's the database server doing with these queries that it receives? Again, we kind of introduced all of this yesterday, so this is just a memory refresher. Excuse me. But what the database is doing is it has to follow a number of steps in order to process that query and then send the result back. This is how Bruce visualized it. Here's how I would visualize it, kind of putting it a different way. And this is, you'll pick this up from that parse page in the docs too, that there are basically 5 steps that the database has to go through to process the queries and send the results back. So it has to parse it, analyze it. There's a rewrite step we talked about. Then it plans, and then it executes the query. And when we talk about reusing execution plans, the thing that we're all concerned about is that plan step. And the reason that matters is because the parse, analyze, and rewrite tends to go pretty quick. It's pretty easy to store. This is kind of tricky. First of all, planning sometimes can take a long time. When I say a long time, this is relative. If you have a SQL statement that's executing that runs very quick, like just a single key lookup based on an index into a table, that thing might run in like a millisecond, right? And if you're running that millions of times, like just select over and over again, millisecond, planning could also take a millisecond, right? So when you have a situation where you have a SQL statement that runs for a very short duration at a high frequency, this plan time suddenly becomes a very large percentage of what your system is doing. Like if you were to profile your system, profile your database and operating system, and look at what it was doing, you'd say, oh my goodness, like half of the CPU is planning on that kind of a box. And the thing is that like when you're doing that, there's no need, right? That you do need to execute over and over again, because I'm maybe running with primary key number 5, and then I'm pulling the record for primary key 20, and then I'm pulling the record for primary key 2001. But the plan's not changing. It's the same plan every time. So like why do we need to always go through that step of planning? So every database deals with this, right? This is something, certainly like in my years working with Oracle, that was very important there to sort of pay attention from a performance perspective. In Oracle, we talk about hard parses and soft parses. There's a section of memory called a shared pool that stores cached plans and tries to reuse them. There's a lot of sophistication around that. Postgres also absolutely does have the ability to try to get you in a place so you don't have to do all that planning. But it works very differently from other databases, and that's why it's really important for me to just take a moment and kind of walk through how it works in Postgres. Now, In Postgres, it is done at sort of the server side. So just real quickly, going back here, and this was something that I was mistaken about in the past, and I kind of realized that I had it wrong. But the optimization to be able to not plan and just do execution, that happens in the database, not outside of the database. So it's in the database. And where exactly is it happening? So this is where, with Postgres, so I'm going to dig right into the details of how it works. First of all, Postgres only does this with prepared statements. There's another name for prepared statements. I've heard people call them. I can't remember what it was. But a prepared statement is, I know I've done them in Java. They're actually called prepared statement. Basically what you do is you have variables, parameterized, sometimes people call them, but you have a SQL statement and then you put these sort of placeholders in the SQL statement. And then what you can do is you can pass that SQL to the database engine and say, parse this, and then get a handle. Okay, and that handle comes back, and then you make a separate call to say, now execute it, and you pass some values in to put into the variables, and it'll just execute it with those variables. And then you can say execute again, it'll execute again with different variable values. That's a prepared statement. Now, in some other database engines, they've come up with ways to be able to reuse execution plans even when you're not doing prepared statements. In Postgres, you will only be able to reuse your execution plans if you're using a prepared statement. And furthermore, like you can start reusing execution plans, but if the way a prepared statement works is you prepare it, and then you can execute as many times as you want. And then when you're finished, you can deallocate it, and that frees the handle and that frees the memory back on the server that you're connected to. If you deallocate it, and then you prepare the exact same SQL statement again, you don't continue with the plan reuse. You kind of just start over from square one. You can get there again, but you sort of like lose it. So you have to have a prepared statement. You can't deallocate it. And then here's kind of the way it works. There's a branch here. If you can do a prepared statement with no variables, that's fine too. It's going to take like 2 calls instead of 1 to run your SQL, because you can run it with a single call, or you can say prepare execute. Okay. If you don't have parameters, Postgres will immediately be like, oh, this is a prepared statement. And just Postgres is smart enough at that point that it will go all the way to the planning phase, and it creates something that is called a generic plan. That's important terminology in Postgres. You have generic plans, and then you have non-generic, sometimes maybe normal, custom, kind of the regular plans that you get. A generic plan means that you're getting reuse. It's a plan that can be reused over and over by a prepared statement. So if there's no parameters, immediately goes to a generic. It's going to compile it. It's meaning that it's just going to store the plan in memory, and every time you execute, it'll never have to rerun that planning step. If you have variables, though, it's a different story. Why would that be? Anybody? Well, I won't have you guess. The reason it's a different story is that when you have variables, things can go very badly. Let's imagine the situation where I have a table, and let's say that in this table I have an index on the country that you live in, okay? And let's say that all of us are in this table, all right? So in this table, let's say that we have a room and there's like 500 people in this room with us right now, and me, all right? And it has like the country that you call home. And in this room, all of us are in this table, and my record is going to say United States. Probably most of the records in this table are going to say Ireland, right? So I have an index on that column, right? And I say, give me all the records from this table where home country is United States. What's the right thing to do? Use the index. But let's say that I say, give me all the records from this table where the home country is Ireland. Do you want to use the index there? No. If you tried to use that, you could use the index, it would work, but it would be much slower if you use the index, you're going to sit there and bounce back and forth. Index, table, index, table, index, table. You're going to go, you're going to go from the index to one block in the table, from the index to another block in the table, from the index right back to the same block that you were in before. And if it happened to get pushed out of the cache, you have to reread it from disk a second time. Whereas, what's the right thing to do? The right thing is, well, I know that like 90% of this table is Ireland. So just read the table and throw away the 10% that I don't need, right? That's the fastest way to do that. So you have a data distribution situation where you don't necessarily want to have the same plan. Now, in some databases, you have the ability to sort of have like child plans. You have multiple plans under a single sort of master plan. Postgres, at this point in time, is not yet that sophisticated. But what Postgres will do is that it doesn't, if you have variables, so if the query just comes right out and says where home country is United States, Postgres is like, oh, well, that's easy. It's never going to change. It can't change because it's all hard-coded. So that's why it goes straight to a generic. But if it says where home country equals variable, then Postgres is like, whoa, 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 whoa. I don't know what's the right plan yet for that because I don't know whether the right plan is the index or the full scan. And so I'm not going to use, what Postgres is going to do is it's going to, at first, it's just going to continue planning every time. So you're not going to get any reuse. It'll go all the way to the rewrite phase, and it'll store it there, store the data. But then every time you re-execute, it's going to replan. It's going to do that 5 times. And this is a hard-coded number in version 11, at least, of Postgres. It'll go 5 times. On the 5th time, though, it will do something a little different. On the 5th time, it'll say, well, how expensive is it for me to figure out the plan and to execute it? And then it'll say, how expensive if I were to make a generic plan without looking at any statistics? So, well, I don't even know which way that generic would go. I'll have to take a look. But it'll say, if I were to make a generic, then what would the plan be and how expensive is that? And it'll compare them. The 5th time it'll compare. If the generic is cheaper, then it'll shift gears and it'll actually store the generic. But if the generic is not cheaper, then it does not. The thing with Postgres, and the thing that you really have to look out for with Postgres, is that once it makes that flip, it never goes back until you deallocate the prepared statement, until you start over. So what that means, if you think about it, is that let's just suppose that I have a query where I do, just going back to our example, give me everybody whose home country is United States, and home country United States, home country United States, and then I say home country India, and then I say home country Australia, home country United States, right? Postgres is going to keep on, it's going to keep on doing what it does, and then we get to execution number 5, keeps running the same thing. But then let's suppose Postgres is like, oh, let's switch to a generic. Okay, so it switches to the generic, but then we keep going. We say home country United States. Then we say home country Ireland. But because we've locked in a generic, now suddenly we're in that place where we're using the index to go pull all the people who have home country Ireland. And suddenly you've got a very bad execution plan that you wind up using. How do you know if you have generics? The way that you can tell if you have generics is you'll see this $sign and a number inside of the query text. I've seen that. I believe you can see it in pgstat activity. I think you might know. I'm not sure if you'll see it in pgstat statements. I don't think you will see it there. You might, though. I need to double check that. You certainly can see it in your own session. So it's very easy to kind of illustrate this by running a query and then doing explain analyze on that query, and then run the query like 5 or 6 more times after doing a prepare, and you'll see the $1 start to show up in your explains. So that's how you know if you're getting the execution plans. And that wraps up my first section that I have for today. Let's stop for a moment